Okay, in this video we're going to talk about the periodic properties of the trig functions. So in an earlier video we talked about coterminal angles. So coterminal angles are pretty strongly related to the periodic properties. We'll see how that's true in this video. And then in the next few videos we'll do some examples with using periodic properties to evaluate trig functions. Okay, so definition here. The period of a function f is called, or it is the smallest positive number p such that f of x plus p equals f of x for every x in the domain of f. Okay? So in other words, if you take any x and if you add the period to x, then you're just going to get the same function value. Okay? So functions that have this property, they're called periodic. So f is called a periodic function. Or more specifically, we could say that f is a p-periodic. Okay, so we can say f is a periodic function or it's a p-periodic, where p is that number. P is the number of the period. Okay? So it is important that we take p to be the smallest positive number because, you could, if you add p again, so like f of x plus p equals f of x, right? Well, you could add p again, so you can have f of x plus p, right? So if you add the period, so here, f of x plus p equals f of x, well, f of this plus p equals f of this, right? But that's just the same thing as f of x. So what is this though? F of x plus p, that's f of x plus 2p, okay? That's f of x plus 2p. So the point I want to make is that if you have this period p, there will be larger numbers that satisfy this equation here. So f of x plus 2p equals f of x. Okay, that's what we just saw here. F of x plus 3p equals f of x, and so on and so forth. But the point is, by the definition of the period p is the smallest such positive number that satisfies this. And this will make more sense when we see concrete examples here. So let's look at the trig functions, and we'll revisit what we just talked about in terms of actual numbers. So if we want to look at the trig functions here, let's do something kind of similar to what we did in the previous video, or in one of the earlier videos with coterminal angles. So x-axis, y-axis. Okay, so let's say we have our unit circle here. Oh wow, alright, we'll just pretend that's a circle. So if we have an angle, let's say we have an angle here. Okay, so this is our angle theta right here. Okay, so theta intersects the unit circle. Theta intersects the unit circle right at this point, right? So remember when we talked about coterminal angles, what's a coterminal angle? So if two angles are coterminal, if they have the same, if they're in standard position, first of all, and if they have the same terminal side. So this angle theta, we can go all the way around one full revolution and then back here, and that could be theta plus 2 pi, right? Why is that theta plus 2 pi? Well, if we go all the way around, that's 2 pi, and then we go, let's zoom in a little bit on this. Okay, so here's theta from the x-axis up to here is theta. Well, first, if we go all the way around, that's 2 pi, right? And then we go a distance of theta, so that's 2 pi plus theta, or in other words, theta plus 2 pi, okay? So these guys are coterminal. We can do it again. We can go 2 full revolutions and then up theta to be here. So that'd be theta plus 4 pi. We can go theta plus 6 pi, theta plus 8 pi, and so on and so forth. We could just keep doing that. We could also go the other way. Okay, so we could go back like this, okay, back like this, and this would be theta minus 2 pi. Okay? Why is that theta minus 2 pi? Well, imagine starting at theta, and then if you go back one full revolution, that's going to be theta minus 2 pi. Okay? But just remember we do start here on the positive x-axis because we're in standard position. Okay? So, but you can think of it as starting at theta, and then you go one full revolution in the clockwise direction. So that's going to be theta minus 2 pi. Okay, it has that magnitude, or that size, so to speak, but we do start over here, okay? But it is going to be theta minus 2 pi, okay? So, coterminal angles, we talked about in an earlier video, you add or subtract 2 pi radians or 360 degrees as often as you want to keep getting coterminal angles, okay? And what's special about them, well, coterminal angles hit the unit circle at the same point as each other, okay? So theta plus 2 pi, theta plus 8 pi, theta plus 4 pi, theta minus 2 pi, they all hit the unit circle at the same point, okay? And what does that mean about their trig functions? it means their trig functions are all the same as each other. So the sine of, and what that means is the sine of theta is the same as the sine of theta plus 2 pi. It's the same as the sine of theta minus 2 pi. It's the same as the sine of theta plus 8 pi. Same thing with the cosine and the tangent and the secant, cosecant, and cotangent. Okay? So for example, like the cosecant of theta is equal to the cosecant of theta minus 2 pi. And it's equal to the cosecant of theta plus 2 pi. And again, the reason is because these trig functions, they're defined in terms of the point that the angle hits the unit circle. Okay? And if these different angles hit the unit circle at the same point, then their trig functions should all be the same, evaluated at each of these angles, right? So we'll do some concrete examples in the next few videos, but just know that, remember that when you, if you get a coterminal angle, so first of all, just add or subtract 2 pi radians or 360 degrees as often as you want to get coterminal angles. And remember that the trig functions of an angle are defined in terms of that point where we hit the unit circle, right? So if two different angles hit the unit circle at the same point, then the trig functions evaluated at those angles will be equal. So the sines are equal, the cosines are equal, and so on and so forth. So let's go ahead and write that down. So this tells us what the period is, right? So it's so theta, if we go around one full revolution, theta plus 2 pi, we're back at the same point. Okay, so that's actually telling us that theta plus 2 pi, the trig function evaluated there is the same as the trig function evaluated at theta. Okay, so in other words, what we're saying is, like for example, the sine of theta plus 2 pi equals the sine of theta. Okay, same thing with the cosine. The cosine of theta plus 2 pi equals the cosine of theta. Okay. And not just plus 2 pi, but you know, plus 6 pi, plus 4 pi, plus 8 pi, plus 122 pi, minus 2 pi, right? It's all the same. But as it turns out, for sine and cosine and secant and cosecant, 2 pi is the smallest such positive number that satisfies this. Okay? So what that means is that the period of sine and cosine and secant and cosecant, the period is 2 pi. So remember the definition of the period over here, the smallest positive number p such that this holds true. And as it turns out, 2 pi is the smallest positive number that satisfies this for sine and cosine and secant and cosecant. Okay, so let's make a little chart. So these are going to be our 2 pi periodic functions. So let's say period 2 pi. Okay, notice we're leaving out tangent and cotangent because their period is actually different, which we'll see. So period 2 pi. Sine, okay, let's write it like this. What I want to write is sine of theta plus or minus, or let's just say plus 2k pi equals sine of theta. Okay, let's erase this. Okay, remember this k, I think we talked about in an earlier video. K is just any integer. So what that means is just take any multiple of 2 pi. Okay, take 2 pi and multiply it by k. All right, that's going to give you some multiple of 2 pi, meaning 4 pi, 6 pi, 8 pi. K could be negative, so it could be negative 12 pi, negative 14 pi, negative 2 pi, negative 4 pi, etc., etc. So this just gives you any coterminal angle, basically. Okay, so theta plus 2k pi equals cosine of theta. Cosecant of theta plus 2k pi equals cosecant of theta. And secant of theta plus 2k pi equals secant of theta. Okay. All right, now what about, so first of all, we're expressing this in terms of radians, so we could also talk about it in degrees, right? So if you want to talk about it in degrees, you could say, for example, sine of theta plus 360 degrees times any integer equals sine of theta. Okay. So just want to point that out. I'm just going to express them in terms of radians though, but just remember that 2 pi radians is 360 degrees. Okay. So sine of, if you take an angle theta in degrees, add any multiple of 360 degrees, okay, including negative multiples. So k, remember k is any integer, so k can be negative. Then you'll just get sine of theta again. Okay. So this is really useful for evaluating much larger or much smaller angles, because what you could do is find a coterminal angle that's on the unit circle. Hopefully, if it's a special angle, you could find a coterminal angle between 0 and 2 pi, basically, or between 0 degrees and 360 degrees. And then you could use that to evaluate the trig function. So we'll do quite a few examples with that, some simple examples in the next few videos, and more complicated ones later when we talk about more, after we've talked about other things with trig. So anyway, just remember degrees also, we can express these in terms of degrees. So anyway, and remember, k is any integer. Okay, so that means 1, -1, 2, -2, 0, 3, -3, 14, -14. So we'll just get any integer multiple of 2 pi. So, you know, like if k is 3, then that would be theta plus 6 pi. So we'd go around 2 pi, 4 pi, 6 pi, and then back up to theta. Okay? So that's theta plus 6 pi, for example. So this just means, remember, we talked about this a little bit with the coterminal angles here. So this just gives you any coterminal angle for theta. Okay? So sine of theta, cosine of theta, cosecant of theta, and secant of theta, these all have period 2 pi. So remember what we say is they're periodic functions, or since the period is 2 pi, we can call them 2 pi periodic. So these guys are 2 pi periodic. Okay, 2 pi periodic. Okay, now notice we left off tangent and cotangent. Why is that? Well, first of all, notice that this is also all true with tangent and cotangent, but as it turns out, 2 pi is not the smallest positive number that satisfies that for tangent and cotangent. Okay, so remember the definition of the period says that the period has to be the smallest positive number p such that all this is true. Okay, and as it turns out, for these 4 trig functions, 2 pi is the smallest positive number that satisfies that. Okay, but for tangent and cotangent, there's a smaller number. Okay, so let's see what that's going to be. Let's erase this picture and draw another one, and we'll see why there's a smaller such number. Okay. Oh, by the way, we just kind of glossed over the fact that for these 4, 2 pi really is the smallest such number. It's kind of hard to prove that in general, but you know, you could just try evaluating it with smaller and smaller numbers, less than 2 pi, but you can just kind of tell from the definition of the unit circle that if you're on a different point, you can just know that, remember, when we looked at the unit circle, remember, cosine of theta is the x-coordinate, sine of theta is the y-coordinate, and you know, you'll have the same x-coordinate here and here, like for example, but this distance here, okay, this the angular distance, okay, this rotational distance is not really the same from here to here as it is from here to here. Okay, so it's not really consistent like that. So the smallest positive number p that gives you consistently the same cosine, consistently the same sine, consistently the same secant and the same cosecant, 2 pi is the smallest such number. Okay, so yeah, you can add a smaller number to this guy and get the same cosine and the same sine, but that number that you add to this guy is not the same as the number you add here. Okay, so remember, this period p has to be the same for every x. Okay, so yeah, you might be able to find smaller numbers that work for some x's. Okay, you can find smaller numbers that work for some x's, but the period has to be the smallest number p, the smallest positive number p that works for every x. Okay, not just some of them. Okay, so that's also important. This number p has to work for every x, not just a few of them. Okay. Okay, so now let's talk about tangent and cotangent. Okay, so x-axis, y-axis. Let's say we got our big old unit circle here. A little better. Kind of off center. But anyway, just unit circle, center at the origin, radius 1. So let's say we have this angle in standard position that intersects the unit circle right here, and this will be the point x comma y. Okay. Now this here is theta. Okay. Now what I want to do, let's zoom in a bit on that. What I want to do is look at theta plus pi. If we take theta and add pi to it, remember pi radians is 180 degrees, right? So what's that going to do? That's going to put us over here, which is going to give us a straight angle with theta. Okay. So that's going to put us right here. So what that makes is actually a straight line. So this is theta plus pi, okay? And this theta plus pi gives us a straight line right here, right? So here's the origin. Vertex is at the origin. Both these guys are in standard position. So here's theta. Add pi to theta. We're just going to be at this opposite end of the straight line here, right? So that's all we have here. Now, what are the coordinates of the point here? Okay. Well, you can think of this as a reflection through the origin. Okay. So since this is just a straight line, if I start at this point 0, 0, I have to go over x and up y to get here, right? I have to go over x and up y. Well, what if I want to go back down here? Since it's just a straight line, I have to go over x in the opposite direction, and I have to go down y, okay? So to get to this point from the origin, I go right x, up y. Right x, up y. To get to this point from the origin, I go left x, down y. Left x, down y. So that means the coordinates of this point are negative x, comma, negative y, okay? Negative x, comma, negative y. Okay, so how's that significant? Well, now notice what is the tangent? Okay, so I'm probably going to run out of room here. But what is the tangent of, let's put it over here. What's the tangent of theta plus pi? Okay. Well, the tangent of theta plus pi is going to be the sine of theta plus pi. All right, I'm totally out of room over there. Tangent of theta plus pi is going to be the sine of theta plus pi divided by the cosine of theta plus pi, right? So just remember that tangent of a thing, no matter what that thing is, it's sine of that thing divided by cosine of that thing. Okay? So we know tangent of theta is sine of theta over cosine of theta, but it's not true just for theta, it's true for anything really. Tangent of anything is sine of that thing over cosine of that thing. Okay, so tangent of theta plus pi is sine of theta plus pi over cosine of theta plus pi. What is the sine of theta plus pi? It's the y-coordinate where the angle theta plus pi hits the unit circle. What is the y-coordinate? It's negative y. Okay, negative y. Yikes. Cosine of theta plus pi is the x-coordinate where theta plus pi hits the unit circle. What's the x-coordinate where theta plus pi hits the unit circle? It's negative x. Okay. What is negative y divided by negative x? Well, the negatives just cancel each other out, right? And we're just left with y over x. What is y? It's the y-coordinate where theta hits the unit circle. What's x? It's the x-coordinate where theta hits the unit circle. What's the y-coordinate where theta hits the unit circle? That's the sine of theta. Okay. So if we come up here now, this equals the sine of theta divided by the cosine of theta, right? Which in turn equals the tangent of theta. Okay. So let's recap. So basically what we've just shown is that the tangent of theta plus pi equals the tangent of theta. Okay. So let's recap that real quick. Tangent of theta plus pi, just by definition of tangent, okay, or that quotient identity, tangent of theta plus pi is the sine of theta plus pi divided by the cosine of theta plus pi. Okay. What's the sine of theta plus pi? That's the y-coordinate where theta plus pi hits the unit circle. What is that y-coordinate? It's here, negative y. Okay. Theta plus pi hits the unit circle here. Okay. Cosine of theta plus pi, that's the x-coordinate where theta plus pi hits the unit circle. What's the x-coordinate there? It's here, negative x. And remember, why is this negative x, negative y? Because, well, we just called this point x comma y. So if we start at the origin, we have to go right x and up y to get there. So since theta plus pi just makes this a straight line, then to get to from the origin to here, okay, since we go right x and up y to get here, we have to go left x and down y to get here. So left x means negative x, down y means negative y. Okay, so that's why that's negative x comma negative y. Okay, so continuing here, so sine of theta plus pi is negative y, cosine of theta plus pi is negative x, negative y divided by negative x, the negatives cancel, we get y over x. What is y? Well, if we go back to our unit circle here, y is the y-coordinate where theta hits the unit circle. What's the y-coordinate where theta hits the unit circle? That's the sine of theta. What's x? X is the x-coordinate where theta hits the unit circle. What's the x-coordinate where theta hits the unit circle? That's the cosine of theta. So y over x is just the sine of theta divided by the cosine of theta, which from the quotient identity is just tangent of theta. Okay, so what that tells us is that tangent of theta plus pi is the same as tangent of theta. Okay, so while it's true that we can add 2 pi to theta and get the same tangent, 2 pi is not the smallest positive number that satisfies that. It's actually pi. Okay, pi is the smallest positive number that makes that true. Okay, so Let's zoom back out a little bit. Okay, so these have period pi. Okay, so these are going to be tangent, so let's separate these. Tangent of theta plus k pi equals tangent of theta. Okay, so remember, same deal, k is just any integer, so theta plus pi, theta plus 2 pi, theta plus 17 pi, okay, theta plus 19 pi, theta minus 115 pi, and so on and so forth. This is the same as all, if you take the tangent of those, you're going to get tangent of theta, okay? And it's also true for the cotangent, right? Why is that true for the cotangent? We'll show why in a sec here. Basically, the reason is that cotangent is the reciprocal of tangent. Okay, so we established here. Okay, we went through that a couple times. Tangent of theta plus pi is the same thing as tangent of theta, right? So let's erase all this, and we'll do it real quick for cotangent. It's really just because of the reciprocal identity, but we might as well just write it out real quick. So cotangent of theta plus pi equals 1 over tangent of theta plus pi. Okay, or we could have gone through the same argument that we just erased, but with cosine and sine switched. So that would just give us the cotangent instead. But anyway, so we know that tangent of theta plus pi equals the tangent of theta, so that's why this equality is true. Okay, but what is 1 over the tangent of theta? It's the cotangent of theta. Okay, so that's why cotangent of theta plus pi equals cotangent of theta, just because of the reciprocal identity, basically. Okay, so these two guys are called pi periodic. These two guys are pi periodic. Okay, so yes, while it is true that you can add 2 pi to theta and get the same tangent, 2 pi is not the smallest positive number that makes that true. Remember, the period is the smallest positive number that makes that true for every x in the domain. Okay, and 2 pi does satisfy this, but pi is a smaller number that also satisfies that always. And that's what we saw with this circle that we erased over here. Okay. So that's the periodic properties, and remember, these just help you evaluate trig functions. So we'll see some examples in the next few videos. Oh, and also k pi, remember pi radians is 180 degrees, so we could also say things like tangent of theta plus 180 degrees times k equals tangent of theta, okay? Where k is any integer, so if you want to express it in degrees, then 180 degrees, 180 degrees, these guys would all be 360 degrees because it's 2 pi. So just remember, k represents any integer, so any integer multiple of 2 pi, meaning 2 pi, negative 2 pi, 14 pi, negative 136 pi, and so on. Here, this is any integer multiple of pi, so that's pi, 2 pi, 3 pi, negative 4 pi, negative 5 pi, 17 pi, negative 324 pi, negative 325 pi, and so on and so forth, okay? Just remember, k is any integer, including negative integers. So we'll see some concrete examples with actual numbers in the next few videos, okay? So just remember, oh, that thing we were talking about earlier when we said f of x plus p. So f of x plus p equals f of x plus p, right, equal f of x. So we said we'd revisit that with more concrete numbers. So for example, p, this period p for these guys is 2 pi, right? So let's revisit this with the concrete numbers. So hopefully it'll make a little more sense. So sine of theta plus 2 pi, okay? We know that that's the same thing as sine of theta, right? But what about sine of theta plus 2 pi plus 2 pi, okay? Well, the period is 2 pi, meaning if you take anything and add 2 pi to it, you're going to get the same trig function back, okay? So sine of a thing plus 2 pi is the same thing as sine of that thing. Sine of this thing plus 2 pi is the same thing as sine of this thing, okay? But what is sine of this thing? Well, it's just sine of theta, okay? But if we rewrite this is sine of theta plus 4 pi, okay? So I just want to point out that, there's only one period, okay? There's only one smallest positive number p that satisfies this, but there are infinitely many numbers that satisfy this equation, but only one of them can be called the period because only one of them is the smallest, okay? So here 2 pi is the smallest positive number that makes that true. even though there are infinitely many numbers that satisfy it, only one of them can be the smallest. Okay, so that's the point we want to make here, is that there's really only going to be one period for a function because only one number can be the smallest positive number that satisfies that. So, 4 pi also satisfies this for sine, and cosine, cosecant, and secant. 4 pi, 6 pi, 8 pi, they all satisfy that, but 2 pi also satisfies it, and it's the smallest positive number. Okay, so just want to point out these subtle details with the definition there. So anyway, there's the definition of a periodic function and what the period is. And we say it's p-periodic for the period p. So these guys have period 2 pi, they're 2 pi periodic. These two guys have period pi, so they're pi periodic. So examples of using these to evaluate trig functions in the next couple videos.